The Actor Model with Akka.net with Aaron Stannard, Part 2.
The Azure DevOps Podcast is a show for developers and DevOps professionals shipping software using Microsoft technologies. Each show brings you hard-hitting interviews with industry experts, innovating better methods, and sharing success stories. Listen on to learn how to increase quality, ship quickly, and operate well. And now your host, Jeffrey Palermo.
Welcome to the show. I'm Jeffrey Palermo, your host for helping you and your teams move fast, deliver quality, and to run your software with confidence in Azure, all while using everything the .NET ecosystem has to offer. The podcast is sponsored by ClearMeasure, a software architecture company that empowers .NET teams to be self-sufficient and able to deliver world-class results. And they are hiring architects and .NET engineers who'd like a path to become an architect. So go to clearmeasure.com/careers. And finally, be sure to check out the new video show, Architect Tips. Now, this interview was amazing, and there's so much there that we've split it into a part 1 and part 2. This is part 2, so check out episode 172 for part 1. Now, our guest is Aaron Stannard, and he's the founder of Petabridge and Sdkbin, building open source tools for .NET developers to build concurrent and distributed applications. He also founded MarkedUp Analytics, a real-time in-app marketing and analytics service used by over 1,000 developers. And he spent time inside Microsoft as a Startup Developer Evangelist. And so we catch this interview midway. And again, this is part 2, so we are just going to dive right in. And so for application types, for people who are not even familiar with it at all, just correct me if I'm wrong. If they're building a web application or native application or mobile app, they're not going to put it in that. They're going to put it in a backend process that's consuming messages being received from somewhere, right?
Well, you can actually run, one of the things that's nice about Akka.net is it does scale down. We do have people running Akka.net like in Xamarin or Unity applications, like actually on the client. And you can do that. So Akka.net does not necessarily need to be a cloud scale only thing. It can also run locally on a single process. That's what a lot of our IoT customers do, for instance, is they're having Akka.net run usually on like a process line control system that's actually embedded directly into a factory somewhere. So Akka.net can scale down, but what you'd use it for in those cases where you're building locally on a device would be for probably processing network events that are coming in from something you're connected to. So for instance, our customers in like mobile gaming, for instance, they would use Akka.net for being able to process messages being sent over, let's say, a TCP or a UDP socket. And it takes those socket event messages, and that might cause, let's say, your character to go ahead and lose health or something like that. And that would be, and the actors that are running locally on your device would update your UI elements, which actors can also do. They can interact directly with the UI depending on which thread they're basically bound to, which is a more advanced concept that I'm not going to cover here, but that is something that's possible. And then what typically people use Akka.net actors for, so in terms of Petabridge's customers, for instance, like who are commercial users, large, highly available, mission critical like business systems that run in a data center on the cloud are bread and butter.
And it sounds like high scale is also bread and butter, as opposed to just kind of low scale but constantly running.
So yeah, we have different types of work profiles that run. The key is usually high availability, which means that the business has massive problems if the service goes offline for any reason. So regardless of what the workload looks like on it, the key is the system has to be available to respond to work within this time constraint, or there's a major business failure. So for instance, we have a lot of customers in the transportation and shipping industry. They're using Akka.net for one of two functions usually. The first function is if they're, let's say, keeping track of cargoes, they want to maintain real-time track of basically where all those cargoes are, and basically like it's like a workflow engine for each basic itemized piece of cargo. And they need that usually because customers who are waiting on a product want to know exactly where it is. And there might be, as you can imagine, millions of pieces of cargo in flight for each one of these logistics companies. So they need to be able to go ahead and map that. Those systems tend to have fairly predictable load because you're constrained physically by the amount of vehicles in your fleet.
Yeah.
So they can actually a capacity plan for that. But what they can't plan for is what happens if there's a software update that needs to be rolled out while cargo is being tracked. What happens if there's a hardware failure inside one of their data centers? And so Akka.net gives them the ability to decentralize that workload. So there's no single point of failure or single point of bottleneck inside those systems. That's one example. Another example from the sort of shipping industry is keeping track of, let's say, the real-time position of the vehicles, or in the case of we've got a lot of customers in the railroad industry, keeping track of the real-time position of not just the trains, but also the switches and all the different configurations on the route that are on there. So you might want to know, basically, is this switch pointing to the north or south rail, depending on where it's going to go. And they might have to go ahead and coordinate those depending on which train is coming and which time. Again, that's a system that has a fairly predictable load because you can't rapidly scale your fleet of vehicles and drivers all that fast, but the system has to stay available. You can't be in a position where your software goes offline and you lose the ability to signal your rail host. Right. That's pretty important. So you can't really lose the ability to do that. Now, the scaling piece is important for a lot of our other customers. So, good example, we have a ton of customers in finance. That's probably our biggest market segments overall in terms of the Petabridge business is finance, which is a group that has lots of different types of sub-industries in it. So that can include insurance, banking, portfolio and wealth management. And because their problems are so technically similar, I'm actually going to throw sports betting into there. Their problems look very similar to people who are doing algorithmic trading with Akka.net. Just that they tend to handle a much higher volume of lower dollar amount transactions. Okay, betting on a sports book and betting on an order book for a stock market actually look very technically similar. But those customers do actually have scale problems. So for instance, if you're doing online transaction processing, so for instance, we have a lot of people that use Akka.net for clearing credit card transactions and that type of stuff, clearing payments. During Black Friday, you might get a gigantic surge in payments that's 10 times your normal workload. Well, you're going to have to be able to scale that workload on demand and scale horizontally. That's another thing Akka.net and the ActorModel does very well, is because clustering in Akka.net uses essentially a peer-to-peer networking model, which is inherently decentralized. There's no peer that basically acts as kind of the central point of coordination inside that system.
There's no master node.
No master node. It's all decentralized. Every node is basically equal in terms of its stature inside the network. And the way nodes tend to route messages to each other is they tend to use sharding systems or some other sort of hash distribution system where essentially nodes all own mutually exclusive partitions of entities in there. So if I go back to my original MarkedUp example, we had 30 million users. Well, I might partition it using, let's say, a consistent hash router or Akka.Cluster sharding, which uses a consistent hashing underneath it to say, okay, all users with an ID between this value and this value belong to node 1. Then the next equally sized partition belongs to node 2. And then the third partition belongs to node 3. If I spin up a fourth node, we're going to recompute the hash ranges and start distributing some of the actors that were previously belonged to node 1 or node 2 or node 3 to node 4. And if node 4 shuts down again, we're going to redistribute those back. And that's sort of how horizontal scaling tends to work with the ActorModel, is because it's all decentralized, it's very easy to partition and repartition your data and also the flow of information as your network topology grows and shrinks. That's the problem that centralized systems really tend to have in the cloud, is that when you have, let's say, a single master node, that node really can't scale horizontally. It's not built to do that. What you can do is scale vertically, which means you're going to go ahead and add more iron to that node, but that usually requires downtime in order to do it.
Yeah.
And for these customers' use cases, downtime is an anathema. They literally can't tolerate it. So they have to have a way to be able to scale their workloads without compromising the system's uptime, essentially. And so the ActorModel plays very nicely in those scenarios.
Tell me about transport. Is the transport always a queue like Azure Service Bus, or is it ever a web service call?
So the transport between different nodes in Akka.net is programmable, but it's almost always a TCP connection today. So essentially, it's two nodes will go ahead and open a duplex TCP connection to each other, and they form what's called a mesh network in Akka.Cluster, which kind of looks like, if I had to draw a picture, it looks like a spider's web. Every node maintains a direct connection to every other node. This is ideal for the sort of real-time systems that you build with something like Akka.net, because it means that there's no congestion or traffic management overhead built into it. Every node has a direct line of communication to everybody else. The other advantage of this design is that failure detection, when a node crashes or something, is instantaneous. Everyone notices their TCP connection getting blown up at the same time. The downside of a mesh network design is its scale. It means that there's a theoretical upper limit to how big a mesh can grow when you're using connection-oriented protocols like TCP. And the reason why we use TCP in these systems by default is because it preserves message order, which is important for data consistency. So the upper limit when you're using something like TCP would probably be, I think the biggest cluster I've personally seen in the wild was 800 nodes. That was doing online transaction processing. But the theoretical max size would probably be about 10,000 nodes, would probably be as big as you can get. And the real constraint comes from the amount of paged memory every single node needs in order to support all those TCP connections. And when you get 10,000 nodes, if you're doing 512 kilobit per connection, that ends up being, is it 5 or 50 gigs of data? I think it's at least 5 gigs. It's at least 5 gigs of memory. Let me do the math on that. That'd be 5 gigs of RAM per node, just supporting TCP sockets. So that's basically where you start running into basically overhead problems when you get to that size.
But you don't have a customer that's hitting that point.
No,
it's theoretical.
The average Akka.net cluster size is probably about 50 nodes, I would guess.
What transports can you get a message into it? Like if you have something happen on a mobile app or web app, and now now it needs to send something somewhere over some transport.
So Akka.net nodes communicate with each other using TCP, but in terms of the way Akka.net is almost always used, is Akka.net usually talks to something else that is customer facing. And so in my experience, I've mostly used HTTP APIs for that, where I have an MVC controller that holds on to a reference to an Akka.net actor. And when that controller receives a message, it uses what's called an ask operation, which basically allows it to send a message to an actor, and it has a strongly typed response it expects back. And you can, and the ask operation returns a task you can await on. So the controller will just await for that response. And then when that request is completed by the actor system, it'll serve that result directly to the end user.
So Akka.net is the way to handle some type of incoming request. Is it used kind of instead of or with other frameworks like in-service bus or mass transit or the mediator library?
Akka.net's almost always used with something else.
Okay.
Because where Akka.net really is it's a framework for being able to process real-time workloads for an arbitrarily large number of entities. And those can be workflows or any number of other activity types that are occurring. You usually need some sort of interface to be able to surface that capability to your users. And Akka.net out of the box doesn't really it's not very prescriptive in that regard. It's kind of designed to work with something else. So web APIs are one common example that we have a ton of users that use Azure Event Hubs, Service Bus. I personally, in Sdkbin, we're using the Kafka interface for Event Hubs as our primary way of basically passing information between services. And we also have a customer-facing web application that basically is sending HTTP traffic across. We also have a lot of customers that go ahead and consume data through either an end service bus or RabbitMQ is another popular one. And then we also have a lot of users that really love using SignalR actually with Akka.net. Particularly because with Akka.net actors and SignalR, it's very easy to go ahead and have something like a real-time dashboard or a real-time chat system where the actors can just push a stream of events directly into a UI that an end user or a stakeholder is consuming themselves. So we tend to see that pattern a lot as well.
Okay, so let me give you an example. You can tell me if I'm on the right track. If somebody has implemented a real-time WebSocket connection, they're using SignalR, so they've got a process that's hosted on whether it's a web job or whatnot, or it's running somewhere. When they start to scale up and realize, wait a minute, I've got too much traffic, I've got problems, they can introduce Akka and maybe graduate from a system where they were using a relational database and managing state that way to using Akka.net, which manages that growing state differently. Is that right?
Yeah, absolutely. So I'll give you an example. So we have a number of customers in the insurance industry where their initial use case for Akka.net is almost always the same. We've worked with dozens of insurance companies, but the initial use case is usually we need to have a real-time quote generation system on our website for customers who want to get, home, auto, life, maybe business insurance. And we have a complex model for scoring what this user's premium is going to look like. But we need to be able to handle as much traffic as our marketing team can produce on our site. So we need to have a better model for doing this. Historically, what they usually had is, a little web job that basically processes events from a queue and uses a bunch of static rules that go ahead and load up from a database. And they have, let's say, a rules engine that's used to go ahead and compute a price. And that probably worked fine 5-10 years ago. The problem they have now is that their addressable market's a lot bigger. Their products have gotten more complicated, and there's more of them now. And the old system basically is not really able to provide the level of accuracy they need, the level of customization per customer, and it's also slow. It's the other problems that it tends to have. So where a tool like Akka.net can come into the picture is they're going to say, okay, the first thing we need to do is we need to have a much better way of being able to go ahead and customize the way we produce quotes depending on what the user wants to buy and what their situation is. It's like we don't want to use the same set of rules for offering, let's say, a professional liability insurance to a software company that we do for a construction company. They have very different risk profiles. No one's going to accidentally crush their foot or blow up a building programming software, hopefully. Whereas those are things that might happen in a construction company. So they want to have the ability to go ahead and basically differentiate between all those models. And they want to have the ability to go ahead and generate many quotes in parallel very quickly. So they can go ahead and basically use the ActorModel to pull all those rule definitions into memory and to on demand spin up new actors, which are each going to go ahead and run what would essentially look like a scatter gather process where they might fire off some data packets to a bunch of different, let's say, rule actors that all process different rules individually. And it'll go ahead and know which rules to use based on the user's custom insurance profile. All that data can be gathered back into the actor that basically owns the saga for this one individual user and can go ahead and compute a quote in the order of milliseconds. Another really good example of this type of problem is search, actually doing things like real-time price search for an e-commerce website, where you say, I want to go ahead and find, a set of, let's say, these pieces of inventory all under this price. Well, historically, what customers would have used for doing that would be, let's say, a full text search engine built into a relational database, or maybe an off-the-shelf product like Elastic. And for searches where your inventory is statically priced and where your inventory isn't changing all that much, that probably still works pretty well today. If you're in an industry like travel, for instance, where you're selling tickets for flights or hotel rooms, your inventory is what we call highly perishable, which means that a hotel room on this date expires after that date passes, right? You can't sell it anymore. So inventory churns constantly there. On top of that, in order to maximize margin, you need to go ahead and dynamically price it in accordance with, let's say, demand and supply signals. So in those types of industries, search is something so complicated that a system like Elastic just melts underneath all the combinations there. You can go ahead and use things like akkadotnet actors to build a type of graph search fairly easily, where the actors are able to receive dynamic updates as inventory levels change. This could be as a result of other customers buying flights or buying hotel rooms, or another example might be things like concert tickets. That's another example of highly perishable inventory. And you can go ahead and dynamically adjust your inventory levels in your search. And you can also allow your customer to set very wide search parameters, saying, I want to be able to buy a U2 ticket for any one of these 10 cities near me anytime over the next 2 years at this price. Well, you can basically go ahead and try to model something like that in a CRUD system, but it won't work very well. And the reason is it has a high combinatoric search area, meaning that the number of different combinations of things you have to search is so big and so vast that it can't easily be done in sort of a one-off CRUD system like that. What you'd rather need instead is being able to go ahead and load your inventory graph into memory and very quickly check in with all the tens of thousands of actors that own a part of each of those little inventory nodes on your graph. That can basically allow you to turn a query like that from something that takes minutes to run in a system like Elastic to something that takes milliseconds to run in akkadotnet. And we actually do have customers who have done that in some of those industries. And that makes a really big difference on conversion, for instance. So those are some examples of where akka.net kind of makes its way into more traditional, let's say, types of problems that developers look at in a lot of blue chip industries all the time.
Many thanks to our podcast sponsor, ClearMeasure. ClearMeasure is a software architecture company that empowers clients' development teams to be self-sufficient, moving fast, delivering quality, and running their systems with confidence. Whether starting a new project or developing new technologies or techniques, ClearMeasure sets up your team to deliver world-class results. Learn more at www.clearmeasure.com. ClearMeasure, empowering software delivery.
So a developer might get a signal that they need to look at akka.net if they're spending a lot of time in I/O or data lookups or lots of round trips, and they need to get process happening either just faster in general, or they have scale spikes that cause things to go slower than they need them to be on a consistent basis.
Well, on the spike subject, another big area where actors get used is in ETL systems, where you need to periodically run large analysis jobs. So these aren't the same as some of the other types of workloads we've been talking about, where developers are handling requests coming in from users in some sort of customer-facing product. This is more like we have a set of jobs we have to run that can be pretty expensive, but we know when they're going to run roughly. However, we still need to have a way of guaranteeing these jobs complete in a reasonable schedule, and we need to have some way of managing control of the flow so we can guarantee that all these jobs complete in a reasonable amount of time. So, an example of this that I like to pull up is another financial type application. It's called asset line management. This is a problem that occurs. Usually it's banks that have this issue where they're trying to go ahead and analyze a portfolio of paper instruments, usually mortgages or other types of loans. And so this is kind of the fun scale problem they have. So the scale problem is that they need to basically go ahead and do asset line management to figure out what is the value of this portfolio of mortgages and how has it changed month over month. And that's going to include things like how many people completed the mortgage payments, how many are late, and you want to slice and dice it by potentially different dimensions, such as geography. It might be by the type of loan, so commercial versus residential, et cetera. These jobs can be incredibly expensive for a big bank. You might be analyzing 30 million mortgages, And here's the other issue that comes into play is that these jobs probably only need to run the last 2 days of the month. So every single person,
Yeah.
every single analyst, and let's say the risk management arm of a bank is all going to be scheduling a ton of jobs all in this 48-hour period, because that's when they do their reports, is at the end of the month, right? It's not very useful to go ahead and run a monthly asset line management calculation mid-month, because you're missing half your data. So in that case, what Akka.net's going to be used for isn't so much dealing with this like instantaneous demand problem. It's a scheduling issue instead, where we need to go ahead and make sure all these jobs complete. But in order to do that, we have to introduce, let's say, some flow control where this job is going to wait in a queue until we know capacity is available to service it. We might also have some criteria around prioritization of jobs, which one needs to go first. And that might be dependent on, for instance, a CFO gets the CFO of the bank sends an urgent request to an analyst saying, hey, we suspect we might have a repayment issue happening in this sector. I need you to get a report for me for that today in order for us to, potentially you have to go and send out notices to regulators or something that we might have some exposure here. Well, that would be something that a developer would need to incorporate into their flow control system, the ability to say this job is more urgent than other ones, even though they've been previously scheduled. And so we see a lot of different types of, let's say, batch systems that all run on top of Akka.net too. And the real problem that Akka.net solves there is explicit control of where work happens and the ability to go ahead and incorporate new worker nodes being spun up dynamically when a job is being run. And then they can go and shrink all those nodes back down again when they're finished. So it allows you to kind of run these, let's say these sort of ETL jobs in a cloud sort of scale fashion, where you can scale the job horizontally and then spin back down again afterwards, which actually can be fairly, that can be kind of awkward to go and introduce without a tool like Akka.net necessarily. You can, there's a lot of built-in tools and platforms like Azure that will help you do some of that, but what you lose is the ability to reason about more nuanced things like prioritization or starvation in the work queue. And essentially, if you have one job that really needs to be spread across multiple nodes, that can be kind of awkward to manage using a system like Azure Data Factory or something like that. So a tool like Akka.net gives you a lot more fine-grained control over how to implement that type of workflow.
Okay. How close on the network do the servers need to be to participate?
We're introducing in the next sort of, let's say, a minor release of Akka.net multi-data center, like built-in multi-data center support, where you can go ahead and essentially describe what's in which data center. But today we have some customers that have clusters that do span multiple data centers.
Because what I'm wondering, and for whether it's nonprofits or open source projects of sorts, if Akka.net is a decent mechanism to get some crowdsourced CPU, like for people to kind of like opt in and say, oh yeah, I'll install this little program on my box, and then it be a host, or what's the right term, participate in one of the clusters.
Well, for Akka.Cluster, I don't think so. Having, let's say, like a system like the SETI program or Unfold at Home, one of these classically sort of peer-to-peer distributed compute systems, I don't know how well Akka.Cluster would work for that, because of its sort of real-time, high availability nature. Might preclude some of that, because there might be a ton of gossip from, remember that 10,000 node constraint I just talked about? You might butt into that, and you might butt into some other problems. But because Akka.net's transport system is pluggable, and so is its failure detection system, maybe you could rewrite some of that to use, let's say, a custom UDP transport, which eliminates that. Using a UDP transport would eliminate that memory constraint. You could have a mesh network with millions of nodes in a UDP system, but what you give up there is the ability to preserve message order and the ability to send arbitrarily large messages. And you also lose delivery guarantees over the network when you do all that. But you also gain a whole bunch back in terms of performance and general reliability there. But Akka.net could certainly be used to orchestrate something like that. But our default clustering options are kind of more meant to be managed within one data center. Gotcha. But it's within the realm of possibility, though.
Gotcha. Yeah, I'm also thinking with Maui coming up, I think a lot more .NET developers are going to be writing more mobile apps just because it's so much more approachable. And maybe the scale or the performance of the database isn't the issue, but because I'm going over the open internet every time I go back to the server, yeah, maybe I need to just have a model for more, on the device memory, state management.
Well, the ActorModel work can really help there in terms of, let's say, UI events for Maui developers or people building with something like Uno platform or Avalonia. What could really help those developers is the fact that you might have events that are being generated locally by the user, such as UI events or maybe other system events, depending on what your application does. Like if it's monitoring, local file system activity, those types of events might come up, and network events. Akka.net will allow you to go ahead and exercise a great deal of flow control over those. So for instance, one really common type of UI activity, and we actually did this with a Blazor application not that long ago. We embedded Akka.net into the server side component of a Blazor app. One of the things that we went ahead and did there is used Akka.net, or used Akka Streams, really, which is another high-level abstraction on top of Akka.net actors. We use that for doing debouncing. So if I go ahead and accidentally generate, 30 or 40, let's say, mouse move events per second that are raised by the UI, I may not want to have my application code respond to all of those. I might want to have I might want to go ahead and throttle the rate to maybe 1/10 of that. Well, that's something that Akka Streams does really well. I can go ahead and debounce all those events together, where I could go ahead and take all the events that were generated, and I can go and compute for you, let's say, a spline or something showing where the mouse moved. And if you want to go ahead and animate something, let's say you're building a drawing application, which is what we were doing in that case, we can go ahead and basically just construct a spline from all those in one go and render it, which actually basically is much gentler on the renderer than doing every single raw event would be.
Yeah, no, that's a good point.
So there's things like, so Akka.net can be very useful for doing that. Then if you have, let's say, events coming in from multiple sources, you might have UI events, system events, and network events. Being able to prioritize and render those independently on the UI, something Akka.net can do very easily as well. So there's a lot of use cases for it on the desktop. Most of my focus when I give talks or write about it is all on the cloud side of things with Akka.net, because that's generally speaking where most of our paying customers come from. So, we have a very strong commercial incentive to talk about that.
Yep.
But we also, on the open source cadence side of things, have an enormous number of users using Akka.net inside UI elements. And we do want to go ahead and support that, because that's one of the things that makes Akka.net differentiated from something like Microsoft Orleans, for instance, which is our ability to go ahead and actually scale down off the cloud into a local device or into a local system, where we're essentially a lot less opinionated about where Akka.net needs to run than let's say a cloud first system like that. Yeah,
and I'm guessing the footprint is really just dependent on how much state needs to be cached. Is that right?
Yeah, the overhead of Akka.net is fairly minimal from both a memory and a compute point of view. If an actor doesn't have a message to process, then it doesn't use any CPU. It just kind of hangs out in memory. Actors live forever by default, so you have to kill them when you're done using them. We do have an idle timeout that you can use on your actors. It's called a receive timeout. And we use that to go ahead and automatically, like in a really large scale cloud system, we'll use that to say, after an actor's been woken up, if it hasn't received a message for more than 30 seconds, we'll go ahead and use the receive timeout to have it gracefully terminate. That way we're not constantly keeping actors that are not doing any work in memory. That's the way we're able to go ahead and make, let's say, that system I mentioned at the very beginning, the 30 million users per day system. That's how we're able to make that scale, was by making sure we're always killing actors that were no longer needed.
Yeah.
So the footprint is mostly dependent on your use case. There is some overhead from Akka.net at the networking level, because we do require a specific serialization format, which we handle transparently behind the scenes. We require a specific serialization format for Akka.net's built-in messages. It's basically protobuf plus a custom, let's say, way of serializing your actor references, the pointers to actors between different processes. There is a tiny amount of overhead to that, but it usually pales in comparison to what users do themselves.
Oh yeah, for sure. Awesome. Well, man, this is a ton of good information about the ActorModel and Akka. I think there's lots for the listeners to chew on. We'll include kind of the high level links. But in addition to those, are there any resources that we should include or point the users to who want to dig in?
Absolutely. We have a free, I think it's a 17-unit course, and I just dropped a link to it in chat. It's on learn.akka.net.
Gotcha.
That's the link that this refers to. But basically, this is a free course you can sign up for. It'll probably take you, if you want to go ahead and do it all in one sitting, might take you a couple of days to get through all of it. But this is a learn by doing course. And we've had 40,000 developers go through it over the course of about 7 years. So I would definitely recommend checking that out. That would be a useful place to go. Another resource that would be helpful for learning about akka.net would actually be the Petabridge blog is another helpful one. So I'm going to drop a link to that right down here.
Okay.
And we cover a bunch of different topics on there, all about akka.net. That also links into our YouTube channel, which has a lot of resources on it as well. And then lastly, you should also check out, if you go to the official akka.net website, which is getakka.net. If you go to that website and go to the community area, you'll see a link to our GitHub discussions and also our Gitter chat. There's always lots of users in there. You should feel free to go ahead and ask questions if you have any that pertain to your specific use case you're considering akka.net for. That's a good place to get some interactive help there.
Okay.
I'm usually in that chat room. I was just answering someone's question about akka.net documentation right before I joined the chat today. So, and then other members of the Petabridge team are in there too. So that's a good place to get some questions answered.
Nice. And how can people find you?
You can find me at on Twitter is probably the number one place people reach me. My handle is Aaron on the web. Now, aside from that, you can also go to petabridge.com, and we have a bunch of contact forms everywhere on that site. If you go ahead and fill one of those out, that message will usually find its way to me. So,
gotcha. Awesome.
Yep.
Well, thanks so much for joining us on the podcast, all about the Actor Model and akka.net. A ton for our listeners to chew on. So I appreciate it.
Well, thank you very much for having me, and I hope your users appreciate it. And I've found something useful out of the episode.
Oh, for sure. And until next time, keep shipping.
You've been listening to the Azure DevOps Podcast, a show for developers and DevOps professionals shipping software using Microsoft technologies. Go to www.azuredevops.show for show notes and other episodes. On behalf of your host, Jeffrey Palermo, and our sponsors, thanks for listening, and may God bless you.